So this is topic 6 of Edexcel P2 GCSE Physics, which talks about using radioactive materials. So it goes through the ideas of background radioactivity, activity and half-life, dangers of radiation, and the uses of radiation. So we'll go through each of those one by one to make sure you have a good understanding of those. It's the last topic of P2. So background radiation is radiation from a variety of sources. Okay, the majority of the sources are natural. So you've got radon and thoron gas. Okay, they're the most natural sources of radioactivity, as you can see. It comes from the decay of radioactive rock. This gas is released. If inhaled, it can be dangerous and cause lung cancer in high doses. But that percentage that we have in the background in the majority of the places around the world, completely safe. Note that fallout, so that's from nuclear weapons testing, very, very small. Industrial, we're talking about uses in industry, including the nuclear power stations, very, very small. Gamma rays from rocks and things like that, again 14%, not very high. The body actually gives out a significant amount, and you've got food and drink that's in this other area as well. And cosmic rays, very small amount, but 10% of cosmic rays. And the majority comes from radon gas, which is just there in the atmosphere, released from rocks. This varies as you go around the UK, depending upon location. I mean, within England, Cornwall has a particularly high amount of radioactivity. Some areas of France and Canada also have high levels of background radiation. Nuclear weapons testing and nuclear power plants don't contribute very much, as I said. Right, so here we go, activity and half-life. So activity of a radioactive source is how many radioisotope decays in 1 second. It's measured in becquerels, BQs. If you ever see that, don't worry, that just means it's 1 decay per second. And over the time, the activity of a radioactive substance over time, the activity of a radioactive substance will decay, I should say. So let's change that. That's a big mistake there. Substance. Oops. There we go. Yeah, substance will decay. Some radioactive substances will decay very quickly, while others take a long amount of time. So you see, I've got it written right there. So the property that defines how quickly substance decays is known as the half-life. To know this definition, it's come up a couple of times. The half-life of a radioactive isotope is time taken for half the undecayed nuclear decay. So if I started with 80, after one half-life it would be 40, after two half-lives it would be 20. Okay, so you can find the half-life out by looking at a graph. So start with 80, one half-life is 40, so that's 2 days. Two half-lives is 4 days. Okay, so you can draw this line of best fit. You can figure out an average from this if you want to get a very clear reading of the half-life by doing this once, doing it twice, calculating a mean, figure out it's 2 days. They could say at what time will you have 75% of decayed and 25% decayed. Well, you know that must have halved twice, because after one half-life is 50%, 50%. After two half-lives is 25, 75. So therefore we can figure out what two half-lives is and go up and see, and go down, sorry, and see what time that is. So there's many different ways they could ask this. They could do it in grams. Okay, they could just ask it in words. So I'll put it over here in words. But it just says if a radioactive isotope has a half-life of 20 days and starts with an activity of 200, after 20 days it will be 100. After another 20 days, so that's 40 days from the start, it will be down to 50. Therefore, after 60 days from the start, or another 20 days, it will be down to 25. So we can simulate this idea using dice. If you start with 100 dice, you can evolve them out. Anything with number 6 decays, you can keep doing this until they're all gone. If you keep doing that, you end up with the shape graph, just like you get for the activity graph to show half-life. So, dangers of radiation. The main danger of radioactivity is to cause mutations. It also can burn tissue, but the main danger is that it causes mutations to DNA. State that clearly. I just said cause mutations. That's not a good answer. You want to say cause mutations to DNA. The larger the size of the dose, or the exposure, and the higher the exposure, the larger the dangers. So alpha radiation is more dangerous if you swallow it because it's highly ionizing. However, gamma is dangerous from outside the body because it can penetrate in. To minimize dangers, you should never let radioactive sources touch your skin, or point samples directly away from you, and always return them to a lead-lined box when you're done with them. Big changes happened in our attitude toward radioactivity, mainly after Marie Curie, because when radium was first discovered, Marie Curie knew nothing, and she actually died because of radiation poisoning. There were some watches in in the early 1900s that had that glue in the dark, and some medicines that used this luminous paint that was radioactive, and that caused issues as well. Attitudes began to change when these watch painters died, but also the Chernobyl disaster of 1986 and the nuclear attack of Japan in 1945 actually contributed towards our changing ideas of radioactivity. Right, so we need to go through these one by one. We need to for the use of radioactivity. We also need to understand why we use each type of radiation and what sort of half-life will be used for each source. So, first one is household fire alarms. So you've got a weak alpha source. It gives out alpha radiation that ionizes the air, produces a small electric current which is picked up, and therefore it means that everything is fine. When smoke comes in, these alpha particles are absorbed. There is no electric current. The smoke alarm goes off. So when you press the button to test the smoke alarm, you're just putting a piece of paper in here to make sure that no electric current is produced. We want to use alpha for this so that it can actually ionize the air and it actually gets absorbed by smoke. And we want to have a long half-life so you don't need to keep changing the radioactive source in your fire alarm. Irradiating food and equipment. CES uses gamma rays because it can penetrate right through the equipment. You want a long half-life so you don't need to keep changing the source that's doing the irradiation, and what it actually does is it kills microbes and bacteria without needing to put it in hot water, which could damage it. So the sterilizer machine needs to have gamma source that can penetrate, just like I said, a long half-life, so it doesn't need replacing often. Tracing and gauging thickness. Okay, so we've got two things here. Talk about tracing and gauging thickness. Tracing is when you inject a radioactive source into somebody or put it into a water supply to try to figure out which parts of the body are damaged, but also potentially which parts of a pipe have cracks in them. If a water supply had radioactivity within it, then the cracks would let out more radioactivity than when there is no cracks. Okay, if you inject radioactivity into the body, it will get absorbed by areas that are behaving abnormally, and therefore, say, like have tumor growth there. So they choose the correct isotope to do that. So when a radioactive chemical is used in this way, not normally harmful because you have a short half-life on it, and you make sure you use something like gamma, which can penetrate out of the body. So normally gamma, sometimes beta. Less will be absorbed and therefore less damage. When we're gauging thickness, we use a beta source. It gives out beta particles. It's absorbed by a piece of paper and picked up by a detector. The thicker the paper, the less gets through to the detector. So you can gauge the thickness. If you want it to be thicker, if you think the paper's too thin, then too much beta radiation will come through. So therefore, you move the rollers apart. If the paper is too thick and not enough beta radiation is coming through, then the rollers move close together. So these two are linked to cause that to happen. And the last one is a diagnosis and treatment of cancer. So it can be used in tracers, just like we discussed, to find actual cancer cells, but also can be used in high doses to kill cells, but it'll kill all living cells as well, so you've got to be careful. They're very careful when treating patients. They don't overexpose and they target it on the damaging cells. The last thing we need to talk about is the pros and cons of nuclear power, and therefore the issues to do with storage. The main pros of nuclear power is it produces a large amount of energy. It's safe. It's not as risky as people think. It's only when people do inappropriate testing of nuclear power stations that issues have happened. It reduces the need for fossil fuels. It doesn't produce CO2 or SO2. Only when creation is CO2 released. Only in like the creation of concrete do we actually release CO2. Small amounts of nuclear fuels can lead to large amounts of energy, and uranium is relatively cheap and available as things stand right now. The cons are public perception. Currently it's still pretty bad. It's often seen as dangerous, and people believe that living near a nuclear power station is dangerous, and that nuclear waste could leak out and pollute land, which it could, but the chances of that are very low. In the past, some areas have been contaminated with large amounts of radioactivity, so we're talking about Chernobyl there. So people are worried about another incident like Chernobyl. And the Fukushima disaster that also took place. The cost of running a power station is high due to the cost of actually building the plant and decommissioning it. So when you decommission it, it's being switched off to no longer produce electricity. That's expensive to do. The biggest con is the storage of nuclear waste. So the waste from fission can't be thrown away. It can be recycled in very small ways, but nothing major right now. They're very long half-lives, so they can be dangerous and need to be stored away from people. So normally it's done by this process called vitrification. You don't need to know that name, it's just handy to know because it helps describe the process, where the waste is melted with other materials to make a huge form of glass, which is sealed in stainless steel canisters and kept deep underground. So essentially they bury this nuclear waste underground. They can also put them in thick metal containers and bury them underground in tons of concrete as well. And that's to contain the radioactivity. So the big issue is the storage of nuclear waste and where to put it. That's P2 Topic 6 complete, and that's all of the videos on P2. So after completing all this, watching all the revision materials, and working through your revision materials, my first port of call will be some past papers. Have a go at the questions. If you're struggling with some of them, then come back and watch the video for that specific topic and have a go at the questions again. And good luck.